Let me begin with a word of prayer. Dear me, Father, we thank you for this day. Again, Lord, I thank you for these students and for the time to have a break and relax, refresh. And just pray again, Lord, that you'd help us to be re-energized, to finish this semester well, to use each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So we have now entered chapter 6 of McNerney. And chapter 6 let's see here. MCI ERNY. And the title of this chapter, of course, is what? Contact geometry. Now, I've read this chapter a few times, and I can't say that I entirely understand it yet. And that's not a comment on the author, it's just a comment on me. There's something about contact geometry I don't understand yet. And I'm hoping in the process of teaching this that we'll figure that out. Well, I'll figure it out. I mean, you guys probably also have things to learn, I'm guessing. But so he has two sections at the start of this chapter which motivate the idea of contact geometry. First, by studying the wave propagation of light and Christian Huygens' light propagation model, which is an interesting discussion. And then he gives another example of solutions to differential equation, first order differential equation, where basically he gives a mathematical formalization of this thing we do in differential equations by introducing an independent variable. You know, we introduce, to do reduction of order, well, it's not exactly that. It's related to that, but it's not quite that. But basically, he introduces another higher dimensional space where the derivative becomes a new variable. All right, so he trades a two-dimensional problem for a three-dimensional problem, where something which was a differential relation becomes an algebraic relation, and then he studies things on this three-dimensional so-called space of contact elements. All right, and then you can look at curves in this three-dimensional space, and they may or may not relate to actual solutions to the differential equations. Whether or not they do depends on whether or not a particular thing called the contact form pulls back under the curve. All right. I'm not quite ready to really write those things down in detail yet, so I don't want to do that today, because if I do, it's not going to be good. All right, but you should read sections 6.1 and 6.2 for yourself to try to follow along, because they do motivate what I'm doing today, which is section through 6.3. Section 6.3 contains mathematics that I understand fairly well, so I'll share that with you. But the motivation for it, that's the thing that I don't understand entirely yet. All right, so here we go. I will start by talking about a plane field. What was a plane field? It was an assignment of two-dimensional surfaces throughout some space, right? Some sort of smooth assignment. So we could think of it as an assignment of two vector fields which are linearly independent at each point along some space, right? That would define a plane field by taking the span of those vector fields. He points out that you could also describe it as the kernel of a nowhere 0, 1 form in 3 dimensions. And we're mostly in 3 dimensions, as he repeatedly mentions in this chapter. And anyway, so let me just get started with the notation here. Suppose we have a plane field. He writes E, a subset of the tangent to R3, all right? Then, so basically that's an assignment. P assigns E of P, E sub P, for each I guess he's going to look for the whole deal. I mean, of course, you could do these things over some domain, right, if you wanted. But EP, you could also look at as follows. You could look at EP as being x sub p in the tangent space at p of R3 such that alpha of p, all right, of x of p equals to 0. So this, I mean, like I was saying, we could describe EP as a span of a pair of linearly independent vector fields at each point, right? But at the same token, you could describe them as being things which a particular one-form alpha sends to 0. What would we call this then? What would this thing be? Another name for this would be what? We could also call this the kernel, right? Kernel of alpha of P, I suppose, right? And so dropping the P dependence, we could describe a plane field in R3 as the kernel of a one form. Right. And so you have these dual pictures of how to describe a plane field. You can either describe it sort of the hands-on approach, if you will. The parametric approach is by giving a pair of vector fields, which are linearly independent, whose span builds the plane field as you go from point to point. But on the other hand, you could describe it by an equation, right, which would be this kernel viewpoint. And as usual, we have these two different viewpoints. Of course, if you look at this, what would happen with this equation if you replace this with a non-zero function f, right? Alpha of p, x of p, would that still be 0? That's not a valuation, that's just multiplication. I mean, yeah, that's still 0, right? So this e would also be the kernel of f times alpha, just the same. If I take a non-zero function and I multiply it by the given one form which defines this plane field, same plane field, so it's not unique. The differential form, one form, does not uniquely describe the plane field, all right? Assuming f is non-zero, right? Identically non-zero, I suppose. So this gives us a definition. A contact form all right, on R3 is a one form alpha on R3 that is non-degenerate, such that alpha sub p wedge d alpha sub p is not equal to 0, all right, for all p in R3. This means, we say that defines alpha non-degenerate in this world. Of course, what that means, right? I mean, pragmatically, if you wanted, you want an equation which, what does this mean to say that this wedge product is not 0? It means if you take alpha p wedge d alpha p and you feed it any triple, right, any basis, x, y, z, we get non-zero, right? Yes, Sam? I see you have a question.
My brain is confused because they're capital letters and my brain's like,
Oh, okay. I mean, it's R3. We need three things to form a basis. I mean, TPR3 is isomorphic to R3.
Okay, so we could just pick like partial y, partial y, partial z times.
Exactly, yeah.
Oh, so just, okay, never mind. I understand.
Good, good, good. I mean, honestly, sorting through the noise, you guys can already tell me what this means. I mean, this means that alpha wedge d alpha is nothing more than a non-zero function times dx wedge dy wedge dz. It means that alpha wedge d alpha is a volume form on R3 is what that means. Honestly, that's what that means. But what does that have to do with the things I talked about at the start of class that I can't explain to you yet? All right. So this is the contact distribution. So, and he also makes a definition. We say E sub alpha is the kernel of alpha, okay? This is the contact distribution. Contact distribution, I suppose, generated by alpha. What is a distribution? It had that word distribution in mathematics has different uses, different places. In functional analysis, the word distribution is used for a generalization of function. There's, for example, the Dirac delta function is probably the most famous one of these things. It's a generalized function in some sense. This is not that use. This use of distribution is just a term for not one vector field, but a collection of vector fields. All right, so a distribution is not just one vector field, but perhaps a set of them. Right? And, all right. So he says, if you have a domain U, now he's dropping the all of R3 and erasing this and putting U here, basically. U, subset of R3. Knew he'd do it eventually. So if we take U paired with alpha is a contact space, I believe. So a space paired with a contact form is a contact space. In the same sense that a space, that a domain paired with a metric is a Riemannian space, all right? There's some kind of analogy here. Okay, let's look at an example. Following along here. In 6.3.2, he defines alpha sub naught to be x dy plus dz. All right? And this is in R3 with the usual x, y, z coordinates, okay? So this is the so-called standard contact form. Why is that? Well, if we calculate d alpha naught, what do we got? We just got dx wedge dy, right? We all agree? Good. You can do part of the test Friday. Very good. It's definitely part of the test Friday is doing that. Right? Exterior derivatives are on there. Pullbacks are on there. Push forwards are likely on there. You know, stuff that's appeared in your homework. Yeah. Calculate Christoffel symbols, not on there. But it's important that you did it for the homework. It's good. But, I mean, you understand why it's not on there, right? Yeah, yeah. I mean, if it's on there, it's a take-home question. Let's say it that way. That seems friendlier. But anyway, what is alpha? Alpha wedge d alpha, alpha naught wedge d alpha naught is what? It is x dy plus dz wedge with dx wedge dy, which is just what? That's dz wedge dx wedge dy, which you can rewrite as dx wedge dy wedge dz. In other words, it's the usual volume form on R3. So that's why this is called the so-called standard contact form, because it actually generates the volume form in this way. Yeah. What's the contact distribution? Now, he just writes it down. He doesn't tell you how to calculate it. Let's think about how to calculate it. It's not a big deal, is it? But so we're looking for alpha naught, and we're looking for conditions. So let's think about an arbitrary vector field, right? Let's use A, B, and C for its coefficients. A partial x plus B partial y plus C partial z, right? We want that to be 0 for A partial x plus B partial y plus C partial z. To be in the kernel of alpha naught, right? We need that. What is that, though? XB. That's from, if you don't mind, I'm going to write down the alpha naught down here again. It helps me. Right. So if you look at that, this dy is only going to give us something non-zero when it hits partial y. Otherwise, dy acting on partial x, dy acting on partial z are 0. Right? The functions, a and c, they just pull out through the differential. And so what we get xb, and then how about this one? Yeah, plus c equal to 0. So, aha! Therefore, c is equal to minus bx. So our generic for x, capital X, to be an element of the contact distribution, that implies that capital X equals to what? It equals to, looks like a partial x, right? Plus b partial y minus bx partial z. Do we agree? All I did was put then c was equal to minus bx there. Let me work in a less hard to see marker. And, sorry. So we have x then is equal to a times partial x. I guess that's it, right? Plus b times partial y minus x partial z. So this, what I'm working on, like, you could say, well, what is there to do? You've already described the contact distribution. You told me a good description of it. It's the kernel of this one form. That is true, but we'd like to describe it in another way, which is interesting, which is to find a basis for it as a distribution. And that's what I'm doing right now. I'm finding a basis for the distribution of the standard contact form, and we just have seen now that this distribution, E alpha naught, is in fact nothing more than the span of partial x and partial y minus x partial z. Now he writes these, here's how he writes them in the book. He writes them as 1, 0, 0, and 0, 1 minus x. All right? That's the language he uses in this section right here, right now. I'm just deferring back to my, I think of vector fields as derivations, right? So we don't really disagree. Does that make sense? Okay. In the previous section, another interesting contact form that's motivated from the study of, either the propagation of light or studying a differential equation is given from the following. Let's see here. This is example 6.3. Alpha 1 equals to dy minus m dx. Now here, this is on what he calls CR2. So CR2 is the space of contact elements over R2. The idea of this space is, it's like oh, yowzers, not cool. So sorry, guys. Typical coordinates here, something like x, y, m. All right. Think of m as being the slope of a line. So like a picture of CR2 is something silly like this. But that doesn't quite do it justice because, through a given point, you have different lines, right? Like you have this one, but you've also got this one, and that 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 one. Right? So if you allow that, if you want to think about all possible lines going through a point, you can just think of the slopes as being the third dimension over that to pick out the different lines by just saying the slope is the height out of the board. And in some sense, that's what this CR2 space is. It's a set of line elements in the plane. What's that? Non-vertical. Yes, that bothers me. But whatever. He is, what's that? He never, anyway, I have complaints, but I can't, there is precious little written about this topic at the undergraduate level. That this book is trying to do it is wonderful. And I want to understand it. So anyway, all right. Okay, so is this a contact form? Well, what's d alpha? Yeah. Oh, thanks. You got rid of the minus for me. I appreciate that. So, and then what do we do? Alpha 1, right? Wedge d alpha 1, what's that? Oh, okay, so minus dy. So you see that up to a change in notation, this is kind of the...
Oh, you read it that way, then it's fine.
So this is, come on, this is the same as the last example, just... Oh, I did? Oh, I did that, didn't I? And that was... Top, was that, say again? Top is? Oh, okay. All right. So, yeah, fine. It is a little bit different than the last example, but it's not that different than the last example. We changed z to m. All right. But it's a little bit more than that. Well, it's actually, okay, fine. We had x dy plus dz. Now we're looking at, Yes, if you want to think of, right, but so maybe we shouldn't think of it that way. Anyway, the point is, getting past my silly need to make everything the same, it is a non-degenerate contact form, right? And we can calculate this distribution. I'll go through it a little bit faster this time. We're looking for alpha 1 on x, right, to be equal to 0, which is saying dy of x minus m dx of x is equal to 0. So therefore, if we let x equal to, x1 partial x plus x2 partial y plus x3 partial m, what this equation right here says, that x2 minus m times x1 is equal to 0. And so we can keep the x1, I guess, right? So you see we've got x1 times partial x plus m partial y, and x3 free partial m. So my distribution here for alpha 1 is something like the span of partial x plus m partial y and just partial m, which he will doubtless denote as what? In McNerney, this would appear as 1 m0, and this would appear as 0, 0, 1. Yep. By the way, he even has a picture. This is a pretty neat picture. Actually, this is an important picture to really understand. Figure 6.8, he actually has a picture of the plane fields that are generated from the standard contact distribution. This picture here shows you what those actually look like if you envision them as little planes. I'll regret erasing that. All right, example 4. I'm not sure what example we are here. It's got a paragraph here that is bothering me. I'm not sure if we care about it at the moment. 6.1.3. Well, fine. I'm probably going to regret this, guys, but I'll bite. Proposition 6.1.3. So here's something from section 6.1. It states the following: if we have gamma, a curve from I into CR2 with gamma of t equals to x of t, y of t, m of t. All right? And x prime of t is not equal to 0. Well, x dot rather. X dot. X dot of t is not equal to 0 for all t and I. And you can consider the one form, alpha, equal to dy minus m dx. Aha. Hey, we were just considering that one form, weren't we? Whose kernel is, of course, E sub alpha. Yeah, great. Well, he adds E sub p. Good grief. Kernel of alpha of p is E sub p. All right, great. Then, here's the punchline. Gamma is the lift of a curve C in R2 if and only if gamma dot of t is an element of E gamma t for all t and I. Equivalently, gamma is the lift of a curve if and only if the pullback under gamma of alpha is equal to 0. I think this is worth our time. Let's see here. Try to explain this. So here's a picture. Here's R2, right? And then you can kind of envision up here somehow this contact space. It's three-dimensional, right? And you can picture the gamma. Here's like a picture of gamma of t, all right? And so what would the pullback, let's see here how to say this. What would this mean in detail? This right here, what would this condition mean? I'm not actually going to try to prove this. I'm just going to try to talk about it until we understand it. All right. What does that actually mean if we define alpha to be what it is? I mean, that's what we're looking at here. We're looking at the pullback under gamma of what? Of dy, right? Minus m dx, right? How do we actually do that calculation? I think what we're supposed to do, I mean, what I usually do is I say, okay, well, what that means is the differential of the y function composed of gamma, right? Minus, the m function composed of gamma times the differential of the m function composed of gamma. That's how I actually calculate the pullback. I translate the given form back in terms of the substitution of the map, right? I mean, so here the map is gamma. So y composed with gamma is just what we've called y, right? There's an overloading of notation here, so maybe it's a little bit hard to understand entirely, but So this is the y component of gamma, which unfortunately we've also called here. Let me to remove some of the confusion here. Suppose that this is a, b, and c, all functions of time. Then this is what? This is db, right? Minus what? M is what? M is c now, right? And this, oh, I'm sorry, did I do wrong? Oh, X. Thank you. Yeah. Speak up. You guys are not wrong. So that would, with my new invented dA, right? Good. Now this is supposed to be equal to 0, but if we just rewrite this, this means what? This means that dB, dA is equal to what? It's equal to C. Which, of course, if you translate back into the native variables, that's dy dx being what? M. Let me put it into words. If the pullback of that contact form is 0, it says that the third variable in the curve, right, is actually behaving as it ought to be interpreted as the slope of the curve formed by just the first two things in the curve. If I look at the curve parameterized by x of t, y of t, it has slope m of t. Again, we're assuming that we're looking at graphs. Yeah. And that's why it's called a contact form, because it somehow makes contact, if you will. It describes, if we look at all possible curves up here, it picks out those ones which actually correspond to actual curves down here. If gamma doesn't pull back to be 0, that means it can't reasonably interpret that third thing as being the slope, and so it's not perhaps what we're interested in. I don't know if that helps or not, but yeah.
So that in the red box,
Yeah.
three-dimensional
Three-dimensional curve, right? And so, right, so like down here, the points on this one would be like x of t, y of t.
Okay, gotcha.
Yeah. So how would you, the going the other way around is easier. How do you go from a curve in the plane to a corresponding curve, which is the lift of that curve? The gamma is the lift of, let's call this thing gamma tilde or something, I don't know, but the lift of gamma tilde is gamma. So if you give me a gamma tilde, I can easily create a gamma for you. All I do is take y prime over x prime, or y dot over x dot as my third entry, right? That will force this pullback to be 0, actually, when you sort through it. Yeah.
Is that only the case when alpha is dy times dx?
Yes. Yes. So this is specific. This contact space is built to describe the slope of curves.
Suppose something different, it would describe something else.
Yeah, if we had a different kind of contact form, it might be describing some other kind of geometric situation. That's my belief, but I don't understand that yet. I'm just saying that because it seems like a good thing to agree to. But yes, there are other contact structures, and this is we're cutting our teeth on three-dimensional. But the truth is, this idea extends to odd dimensions. You can do more exotic things. Although some things are very different. Like this, one of the things we learn eventually is Darboux theorem, which essentially says that locally there's just one kind of contact structure. They might model different things, right? But Rn plus 1, you want to find the contact form on R2n plus 1 rather, it is up to the equivalences that we'll eventually describe just a specific thing that can be, you can choose a coordinate system where it's just like the standard form as it generalizes to higher dimensions. In contrast, if you give me a Riemannian space, right, and you say, okay, so, is a Riemannian space of dimension n, what's its metric look like? There's lots of different metrics that are possible for an n-dimensional space. There's lots of different and equivalent metrics. So in some sense, it's like if you only had flat manifolds, there would be a strict analogy somehow, because if the manifold's flat, right, that means that you can choose coordinates that make the metric into just the Euclidean metric, at least locally. And curvature being non-zero is the obstruction to doing that. There's no corresponding notion of curvature for contact spaces. So when contact spaces are inequivalent, it has to do with their it has to do with the totality of the space as a whole. So like judging when two different contact spaces are inequivalent is a question of topology, global topology of the spaces, which makes it considerably more sophisticated. This he says many times in the chapter. So eventually it drilled into me. But what I'm actually more interested in, Travis, is understanding how this can be used to understand solutions to differential equations. Because I'm pretty sure that the right way to understand differential equations, like what is a solution to a differential equation? I think probably the right answer to that is it's a manifold. It's a submanifold, and the differential equation is actually a differential form. And to say something's a solution is to say that that differential form, when restricted to the submanifold or something like that, is zero. And that's what it means to be. But you could rephrase that in terms of pullbacks. You could say a solution is something that pulls back that form on the larger space to zero. That would give you some way of describing differential equations without relying on the explicit coordinates. And I think that's in this chapter, but not explicitly. I mean, this is what I'm trying to dig out of it. Let me move along here. I actually had something I was trying to get to. I seem to have drifted back into the section I wasn't going to cover. My apologies. Another one. I'm not sure we need all of these, but just to be safe, I'll write them down. Also, because they're fun and decent practice for Friday. It's here, in some sense. Alpha 2 is dz plus x dy minus y dx. So I'll just write down, I'm not even going to go through it, but if you work it out, alpha 2 wedge d alpha 2, in this case, works out to 2 times dx wedge dy wedge dz. Doesn't he have anything here which isn't just, And he says that you can work out that the distribution here is just the span of, in my notation, partial x plus y partial z and partial y minus x partial z. Of course, it's easy enough to check if his answer's right. Right, guys? How can we check if he's right or not? If we let alpha 2 act on partial x plus y partial z, how's that go? So this should take you back to the start of the course. I mean, we're giving this a different meaning, but if you look at the calculation, my goodness, isn't it the same as the null space calculation we did really early on in here? I think it's always linear algebra if you look at it. How much of this is linear, really? Sorry. dz, so that gives me a y. This, essentially, you could write 0. This hits that and gives me a minus y. Oh, so it's 0. Well, that's good, because it should be 0. Allegedly, they're in the kernel, right? Is example 6.3.5. He finally, well, anyway, again, I have no room to complain. What have I done? All right, so alpha 3 is cosine of z dx plus the sine of z dy. This one's kind of neat. It's degenerate. It's non-degenerate. You can work it out. Again, alpha 3 wedge d alpha 3 is, what does he say it is? I think it's minus dx wedge dy wedge dz in this case. All right. And so what was the contact? So if you look at this, for x to be in the kernel, we've done enough of these that maybe you can start to see how to kind of cut through these a little bit faster. Alpha 3 means that what? It means that cosine of z times the x, the first component of x, plus the sine of z and times the second component is equal to 0. Which is kind of annoying. I mean, so certainly, oh, I know how to solve that. Do you know how to solve that? So kernel alpha 3 is span of, well, first of all, partial z, because that's not even restricted. No condition on, and on the other one, this suggests to me that I can put x1, bless you, is minus sine z, and this suggests to me that x2 is cosine z. Times a constant, I mean, times a function, let's say. But if I do that, then these cancel. And so then that gives me, minus sine z partial x plus cosine z partial y, I believe. Which is what he has. His last example is actually kind of interesting, so I'll skip it. Just kidding. He has one that's it's in R3 in cylindrical coordinates, and so he does the dance of sine r over r being defined for r not equal to 0, and that function being 1 when r is equal to 0, and it involves that. And I think I'm going to go on because I don't want to rush what follows. So, all right. So, you guys have some sense of what a contact form is, all right? I think. I've shown you a little bit about what it has to do with preserving a geometric condition, namely that a curve has a tangent line defined by the derivative of its component functions, right? But I assure you there are future uses. So I'm reading from page 290 at the moment. So I've already pointed this out. The degeneracy condition means that alpha wedge d alpha is a volume form, right? Okay. So he says, we now turn to the more geometric side of the condition. In particular, we will discuss the meaning of the non-degeneracy condition of alpha from the perspective of a contact distribution E alpha. In order to do so, we'll turn to the question of integrating a plane field. All right. So yeah, this is, when I think about plane fields, I tend to start with what I'm about to show you. Oh, okay. Am I that much over?
No, I was actually early.
Oh, okay, that's fine.
Thank you.
Welcome back. Where was I? Oh yes, we don't need this anymore. So here's a plane field. It's degenerating. But my point was, oh, it's awesome. The worst picture of, anyway. So this is supposed to be z equals to constant for various constant, you know?
We're supposed to be the same.
Just we're supposed to be parallel z-planes. Let me hazard a, here's another picture of it. There you go. So, you know, this is actually something that will not appear, I think, as a contact distribution. Let me explain why that is. So he says, consider a smooth function. So you have to bear with me here, guys. I'll get the ideas out eventually. Smooth function f from R3 to R. All right? Then if we assume that df, assume that, good grief, I lost my place. df of p is not equal to 0 for all p, then what? He says, then f defines a plane field, E sub f, on R3 in the natural way. So how will we define a plane field, E sub f? So he says E sub f at p, what's going to be? It's going to be the, all right, the tangent space to p of S sub p, which of course is a subspace of the tangent space at p of R3. Let me further elaborate. You're like, well, what's SP? Right. SP here being the level curve, level set. SP, I mean, if you want, you could say it's the inverse image of 0 under F, right? It's x, y, z such that f of x, y, z is what? Now, I don't know if he says it's the level 0 curve. I'm just saying let's use 0 to be specific, okay? So if I have, I mean, the assuming the differential is non-zero gives us that there's a well-defined normal to the tangent plane of the level surface and makes this, honest to goodness, two-dimensional geometric set, right? So we can use that tangent space to the geometric set to define our plane field at P. And so this gives us a way of creating a plane field, right? Completely divorced from this not Mickey Mouse, completely divorced from this kernel calculation thing we've been doing over here, right? So like, for example, this one, my f of x, y, z. Oh, it doesn't have to be 0. I'm an idiot. It's how to say that even? I guess that's the point. He's slipperier than I'm being. It doesn't have to be 0. It's that p has to be in equals to c, right? Containing p. Well, such that f of p is equal to c, if you will, right? So it's the level set which you choose the appropriate level. The level set goes through the point P, right? Like you see that in my example over here. I take my level function to be z. If I want to find, I pick a point in R3, I can find a value for the level function, whatever the z value is here, right? If this is 3, 7, 11, then I make my constant 11. My s sub this point is the level set of 11 for the function z, and that gives me my plane in the plane field. And I can do that for every point in R3. I can pick a value such that z equal to a constant gives me that, You can do this for more exciting things like an onion, right? Like a bunch of spheres. You pick any point, it has a distance from the center, right? So if you look at the function x squared plus y squared plus z squared, you can choose a value such that that being equal to a constant hits that point, which is a particular distance. We can do this for spheres too, right? Like pick any point in the R3, it's on some sphere from the center of the origin. So you can look at f equal to x squared plus y squared plus z squared and do the same thing. It's not just planes. It's more exciting things than that. This condition that dfp be non-zero gives you that there exists a surface, a level surface of f through that point is what that condition is needed for. Okay, so anyway, with that said, EF is what? EF is actually equal to the kernel of df, right?
Oh, so df is non-zero means that you have like level surfaces rather than like degenerating to level volumes.
Oh, I don't know I'm not making a connection just yet. We're getting there. So he says this example then raises the following question, starting with an arbitrary smooth plane field, right? Suppose you're just given a plane field. Can you find it as the kernel? Can you take an arbitrary plane field and write it like this? Given a plane field, can you write it as the kernel of the differential of a function? Given plane field, E, does there exist f such that E is E sub f,
So we have d is df equals, so we don't meet the non-degeneracy condition.
Aha. So what, say that again?
So to meet the non-degeneracy condition, we have to have df wedge d df equal to non-zero, but d df is always zero.
Wait, now exactly. Yes, this cannot be a contact form, can it? Can this be a contact form? As you've just reasoned. Because if alpha is equal to df, then d alpha is d df, which is 0. And so yes, clearly alpha wedge d alpha is equal to 0, which of course is not equal to 0. In fact, it's much worse than failing